and my advisor, Joe Paradiso, the head of the Responsive Environments Group at the MIT Media Lab. And we have to thank Susanne Zeitinger from Philips for generous donation and help us to set up the lighting lab in our space. So this lighting lab is arranged as an office. It has 2 different kinds of fixtures, and downlight and wall wash, and it has 8 different fixtures that can be segmented into 20 different segments. Just some details about the space. All right, motivation about context-aware lighting. Well, light is a very important factor in our lives. It's one of the most pervasive technologies that surround us. And to have a better control over the light, we can create better experience and increase comfort, have maybe change people's mood and have higher productivity. And of course, it's also one of the major energy consumers. So this already being catched on. There are a lot of hardware coming out to the market and being installed in places for smart lighting applications. And now the question is what kind of algorithms we use to control these. And when we talk about control, these are normally the parameters that we can control. So one is intensity, and the other one, if you do have color light, it's color. So if we have more than one, we normally have this kind of controllers like control bank where you can control them individually. But when I walk into a space, maybe like this one, when I set up this meeting before it begins in the morning, I don't want to think about, oh, light group 1 should be this, light group 2 should be this. I rather ask myself the question, okay, it's a technical conference, so we probably want people to be focused on their work. We don't want them to fall asleep, so we set the focus factor to 80%. And then also we don't make people too tense. It's not an exam, so we maybe set the social factor to, let's say, 20%. But not more than that. It's not the wine and wine bar and posters anymore. So that's how I rather set up the space than thinking about which light group does what as not a lighting designer. So the question now is, if we had sliders like that let us control the space that way, how do we actually map the lighting, right? What is the light for focus? What's the light for inviting people to be social? And then the other question is, once we have the mapping to the light, once we can answer these questions, can we use something that automatically set the slider so I don't actually have to go there and set it, so maybe after lunch, the focus factor goes a little higher. In the break, the social factor goes a little higher. So it can automatically adapt to what it's doing. And this is also the moment where we can save energy, because now we are moving away from static lighting that is always constant and bright to something that actually adapts and uses more energy efficient settings when it's possible. All right, so my talk is going to show our answers to these 3 different parts of this question. And basically, the first one would be the contextual axes. So these are the sliders I've been talking about. The second one is the lighting control, how to map it to the actual light hardware. And then the third one would be activity recognition, how to automatically recognize the operating point with the dot on the phone, which is the slider positions. And we are not using sliders. We're actually here using a 2-dimensional pad controller. So you might ask yourself, why am I so obsessed with this kind of axis representation of context? So for the first one, it's more intuitive, right? So more intuitive for someone who's not an expert. So that's what the example I use. I walk into here. I rather use these slicers to be more exploratory and see like how does it actually look like when I set focus to high? How does it look like when I set social to high, compared to being instructional to say, okay, zone 2 should be like this, zone 3 should be like this. And I can also explore a large set of settings very quickly, because now I have this 2-dimensional controller that let me explore almost all possible settings by moving this one dot around, right? Before that, I had to change 4 different controllers in order to control each of the spaces separately. And also, Now it enables a simple set of sensors to manipulate complex lighting scenarios, which means if I'm an application designer to design an activity recognition software, I now don't have to think about what I do with light zone 2 or light zones 3. I just have to say, oh, okay, I have to detect how social someone is and how attentive they are, and then I can control the light. So now I simplified the activity recognition problem. And last but not least, this is actually really important in real life, especially because when you the right-hand side, the lighting control side, are actually questions that that designer for left-hand side, the sensor activity recognition. That's our interest in the computer science community. Not one person can answer this whole question. So now you can imagine some activity recognition or Google Glass for the phone, for wristband. As long as it is giving me some kind of. Whereas on the right-hand side, the lighting designer can now go ahead and design the mapping for this space while it's a conference, where the tables are arranged like this, or a setting for this space when the tables are arranged in the middle and it's more like a dinner scenario, or for a completely different space. So suddenly these pieces can become interchangeable, and they come together through this abstract layer. Okay. And this is really important in real life, because like the Google app designer does not know how my living room looks like, but I do, and I can become the lighting designer of the living room. But the application designer only access to the abstract layer in the middle. All right. So your summary of all of them. And now I'm going to go step by step to explain what we did to answer these questions. So the first one are the contextual axes. So what are these sliders? So we did 2 studies, one in a virtual environment and one in a physical environment. I'm going to focus on the physical environment in this talk. So we invited a lighting designer to design 6 scenes for this lighting lab for our space. And by varying color temperature and 6 lighting groups in the space. And the lighting designer had some knowledge about what are the things that will be performed in the space. And you can see on the right are the 6 scenes. They are actually more exaggerated. So the dark scene is not actually that dark. Our eye has much more higher dynamic range than the camera. So this is all shot with the same settings. So there's a warm down light, warm wall wash, and the gallery light, where the lighting is more focused on the pictures, and then the colder settings, and then a presentation setting where it's very low light. All right, and then we invited participants to rate these 6 scenes for their suitability for 14 different tasks. And we chose this task with some kind of dimension in our mind, right? These dimensions are creative, executive, relaxing, demanding, social, individual, visual, non-visual, formal, and informal. So based on these classes, we defined tasks like coffee break, handcraft, CADing on a computer. And we invited 40 participants for the virtual space and then 17 participants for the real space to rate the settings. And then we formed PCA on the preference data to find the underlying dimensions that explains the variance in the preference. And this is what we found out. So we got 3 different axes. We named them attentive, casual, and work with displays. So attentive has things in there such like sketching on paper, handcraft, memorization. And casual has things such as coffee break, casual conversation with a friend. And work with displays has things such as chatting and emailing, etc. And here are the initial 6 scenes put into this component space using the component scores, right? So here we can see, for example, when someone is attentive, they tend to have more wall wash and more colder light. And if someone's more casual but not attentive, they prefer this kind of gallery lighting that has more focus on the pictures and more warm light. And when they are both attentive and casual, they prefer to have the warm light, but still a lot of focus on the walls to have this more public, more spacious kind of feeling. And then work with displays. They also prefer to have more focus on the walls, whereas without displays, they prefer more to have focus on the table. So these are not surprises. These are findings that you can find in large body of lighting and psychology research. And it agrees with many of the previous findings. But what we do have now, what lighting psychology researchers are not attempting to do is we now have this mapping for the space, right? We are not looking for a golden rule to give it to a lighting designer to make choices for the space, but now we actually have the settings of these presets in the space. And this allows us to do the mapping. So as I said before, we were looking for these sliders, and now these principal component can now become our sliders, right? The first one, not surprising, is attentive. The second one is social and casual tasks. So, so since we have these scenes already organized in this control space, we only now need to interpolate between them to create a continuous control space. Right, and we do this by using a weighted superposition where the weight decays with a Gaussian shape. And here in the left bottom corner, you can see the settings of one lighting group for a certain context. So this is now the setup. We created an iPhone app that let you change the operating point, and that operating point is basic feed into this mapping algorithm, which then generates the settings for the lighting room, for the lighting lab fixtures. And I can show you in a video how that feels like. Here we go. Now you can see in the right upper corner, I'm changing the operating point with my finger, and the light in this space changes accordingly. So if I slow this down, you can see here on the bottom, this is now more focused on the table. This is like the less attentive setting, where when it becomes like more focused setting, more attentive setting, it starts to focus on the walls also. And again here, when I set it to a more social setting, it starts to create this gallery lighting with the focus on the pictures. And if I increase this to both attentive and social, it creates this more open kind of feeling. All right. So the next step would be activity recognition. And we chose Google Glass in this case to be our platform to study, to basically create this complete system. And the reason why I chose Google Glass is because head-mounted sensors are really suitable for detecting gaze-related activities, which are most of the things that we are looking at. So there's a large body of really interesting research of using head-mounted sensors, the IMU, to measure head motion and combine it with blinking behavior that you can basically detect what kind of things people are reading and whether they are reading, and also use computer vision and head-mounted camera to see what kind of objects people are engaged in and to understand more what they're doing. Of course, there's also research on voice and tone of voice to see what kind of social situations people are in. So we use only the very basic of these sensors to detect our operating point. To do that, we used the IMU, basically the head motion, to indicate the engagement of attentive tasks, which is the IMU data with the leaky integrator and weighted by the pitch angle, so the more you look down, the more likely you are reading something. And then use the sound to indicate engagement in casual tasks, which in our case was coffee break and casual conversation with a friend. We also used the light sensor for closed loop intensity control to make sure that the light is always in an acceptable level. And of course, people were also able to input manual correction, which will be registered as an offset of the actual activity recognition. So there is some filtering on the input data and mapping, and this will be sent to the lighting. So here is a video that gives you a feeling of how it feels like or how it looks like in the space when someone is actually working, in case this is me. And you can see on the left bottom graph, that's basically the red dot is the operating point moving around, being set by Google Glass in real time. And you can see I'm working, it's moving slightly, but once I start interaction, talking on the phone, it moves more into the casual but still attentive kind of corner. You can also see on top of that the graph that's showing the power consumption while the lighting is changing. So a colleague comes in and just interrupts me, and the light changes to a more social setting. All right, so we did a preliminary study with the system to see where we should take this research now after we have implemented it. So we invited 5 people to stay in the room for 30 minutes to an hour to do their normal work tasks, what they have to do. These are students. And they are in the room with the instructor together, so there can be a social situation. And they are wearing Google Glass. We estimated the power consumption during that time and did an exit interview afterwards. Right, so what we found out, first of all, the simple part is compared to static lighting, and in this case, scene 2, which is the one that's most likely to be chosen if you have attentive and social situation, we achieve 38% of power savings. And compared to the brightest scene, it's 52% of power savings. And this can be explained that because we chose the constant of change very slowly, so the light can change very slowly to more low power settings without disturbing the user at all. And if you go back, well, let me just, so if you look at the setting, the more low power settings tend to be in the center, and the higher power settings tend to be at the edge. And that's why also there's a natural tendency to be more in the center, more at the low power settings. And in the exit conversation, we asked the people whether they thought that the lighting actually supported what they were doing, whether they understood the changes of the lighting, and whether they found it pleasant. All of them found them pleasant and explained or described them as slow and natural and subtle. And they described different reasons why they thought the lighting kind of were responsive or supported them in their task. And one of them is that it gave them indicator of their social state. So when 2 people in the room were sitting and working, it was quiet, and people were focused, it went into this cool concentration light. And that's the moment when they know, okay, both people have agreed on working in this room, so I should not interrupt the other person, and they tend to stay in that state. And once they start talking and interacting with each other, and the light slowly went into the orange or a more social kind of situation, they're reminded, oh, maybe I should go back to work because now I revealed myself, I'm not working. So actually 2 out of 5 people performed manual correction on this, on the lighting. So what did we learn? The speed of adaptation is really interesting, so this should definitely be a factor that should be studied further. And it's also really important for the behavioral feedback, because that is actually the one that controls kind of what this contextual inertia does. And this has to be studied in a longer study and a less controlled environment. And also we saw 2 people out of 5 actually change the lighting, so we should incorporate individual preference, and this should, I think the best way to do this is to learn from these manual corrections over time. And then definitely multi-user, multi-objective optimization. This time it was just only one person wearing Google Glass. And then also there's questions, can we get rid of the initialization using the survey and instead using a sensor-based initialization? Okay, here's the conclusion. So I introduced a novel mapping strategy for context-aware lighting that introduced this abstract layer of these axes. And this way we enable a simple set of sensors to manipulate complicated lighting settings. And also we implemented the system and showed in a preliminary study that it can save up to 50% energy and showed some possible future research direction including behavioral feedback. Thank you, and I'm happy to take any questions.